Hello folks, and welcome back. Today we're going to be working on assignment 12, section 3.5, and we'll be learning what the derivatives of the 6 trig functions are. So let's begin by talking about sine and the derivative with respect to x of sine of x. Now what we want to begin doing is just a graphical understanding of what this derivative might be. And so what we'll do is bring in a picture of the sine graph and see if we can figure out what the derivative might be from that. Okay, so what we have here is a nice representation of the graph of sine, and we would like to see what its derivative looks like. So what we'll do is we'll look at those places, the obvious places, right here and here and here and here and here, where the derivative is 0. Because there's a horizontal tangent. So we know that we'll have a point right there, and a point there, and there, and there, and there. Now, let's look at this point right here. That looks kind of nice, and if life is really good, it could very well be that right there the slope of the tangent line is 1. And here the same thing. And it could be that right here, if life is good, and there, if life is good, it looks like the slope of the tangent line, the derivative is -1. So if we put in those points, here's what we get. Here it looks like the slope is 1. Here it looks like the slope is -1. Here it's 1. Here it's -1. And if I connect those points, if I do it correctly, we get something that looks like this. Bang! So what does that graph look like? Well, I hope you can see that it's pretty clear that that graph could very well be cosine of x. Now, that's not a proof that the derivative of sine x is cos x, but it helps us be pretty well convinced that that statement is true. So we'll move on now and we'll try to prove directly that the derivative of sine is cosine. Now, you'll see why we want to look at the graph of the function sine of x over x, which I have shown here for you. It's a kind of interesting graph, and it's pretty easy to understand that as x goes to 0, the top goes to 0, the bottom goes to 0. This function is undefined at 0, but we're very interested in the question, what is the limit as x approaches 0 of sine of x over x? And again, as we look at this graph coming from the left or from the right, it seems pretty clear that even though there's a point of discontinuity here, we really want to show that with an open circle, that from either side the limit seems to be, and is indeed, equal to 1. Now that limit is going to be very, very important for us as we go ahead and look at the actual formal derivative of sine of x over x. So we want to try to emphasize how important this particular limit is. And we'll move along here and we'll look at a related limit, which is this. The limit as x approaches 0 of 1 minus cosine of x over x. Now, again, as x goes to 0, the top goes to 0, the bottom goes to 0, we have an indeterminate form. We could look at the graph of 1 minus cos x over x and come to a similar conclusion as we did for the graph of sine of x over x. But in this case, what we'll do is a slightly different approach, and we'll deal with this algebraically. So what I'm going to do is multiply top and bottom by 1 plus cos of x and 1 plus cos of x. Now, because you're very smart kids and I don't have much room here, I'll talk a little bit about this. When we multiply 1 minus cos x by 1 plus cos x, we get 1 minus sine squared. And you should easily remember, hopefully from trig, that 1 minus, did I say that right? 1 minus cos squared is equal to sine squared. So, I hope I didn't confuse you with what I said. I think I misspoke. But we can rewrite this as the limit as x goes to 0 of 1 minus cos squared, which is the same as sine squared, over x times 1 plus cosine of x. And now if we use our properties of limits, we can break this up as the limit as x goes to 0 of sine of x over x, which we know to be 1 from above, times the limit as x goes to 0 of sine of x over 1 plus cos of x. Whew. Okay, so here's what we know. This limit goes to 1. That's already been shown. Now, how about this limit? If we let x become 0, or get close to 0, the top goes to 0, the bottom goes to, yep, that's right, I heard you, 2, and so 0 over 2 is 0. So what we see here is that this limit is 1, this limit is 0, and so this limit as x goes to 0 of 1 minus cos x over x is in fact equal to 0. And those are the two important results that we need. Alright, so I've written down these two important results, these two limits. Now let's go to work and see if we can figure out, using the definition of the derivative, what the derivative of sine is. So if I take the derivative with respect to x of sine of x, this equals, by the definition, the limit as h goes to 0 of sine of x plus h minus the sine of x all over h. You'll remember from trig that we have an identity for the sign of a sum. And I'll use that identity and I'll rewrite this as the limit as h goes to 0 of sine of x times cos of h plus sine of h times cos of x. And then I have the minus sine of x at the bottom, at the end. And all of that's over h. So again, I'm going to be using some of the properties of limits, and I'm also going to use the fact that sine of x and cos of x are independent of h, and so I can bring them out in front of the limit. So the first kind of trick is to look at the first chunk here and this chunk here and recognize I can factor sine x out. And if I do that, I get the sine of x times the limit as h goes to 0. So I'm left with cos of h minus 1 over h. And then, at this point, I just have this chunk left, and I can take cos x out and write this as cosine of x times the limit as h goes to 0 of, look what we have, sine of h over h. Okay, so now you see why we looked at those two limits. This limit is 0, and this limit is 1. So here we go. This is 0, this is 1, and so therefore what that means is that this limit simply reduces to cosine of x. And so what we've shown here is the big result that the derivative of sine x is equal to cos x. Ta-da! So we know now, we've proven that the derivative with respect to x of sine of x is equal to cos of x. By a similar argument, and using the identity for cosine of a sum, we can show that the derivative of cos of x is equal to minus sine of x. That's always a little surprise where that minus sign comes from. Alright, so those are the two big identities. And once we have those identities, we can find any other one. I'll show you how we use the quotient rule to take the derivative of tan, and then you'll be able to figure out what the derivatives of cotan, secant, and cosecant are. So let's see if we have enough room here for the derivative with respect to x of tan of x, which we can rewrite as the derivative with respect to x of sine of x over cos of x. Right? So we write that as a quotient, and we use the quotient rule. Hopefully it will have enough room. So it is low d high. Oh, I'm not going to have enough room, so I'll start this on the next line. Okay, there we go. So we have the derivative being low d high minus high d low. The derivative of the bottom is minus sine of x all over low squared. Okay, so here's cos squared, and here is plus sine squared. And we know, because we know our identities, that cos squared plus sine squared, this whole top is equal to 1. So what that means then is that the derivative of tan is 1 over cos squared, which is the same as sec squared of x. And we're done with tan, the derivative of tan. Okay, so to summarize what we know and to write down simply what we could have shown, here we have all the derivatives of the trig functions. Derivative of sine is cos, derivative of cos is minus sine, derivative of tan, derivative of cotan, and these two you can easily show by, again, using the quotient rule. And what I ask you to do is notice the way I have color-coded these. So this right here, these are cofunctions. Sine and cosine are the cofunctions. And look at their derivatives. Their derivatives are opposite cofunctions. Similarly, with tan and cotan, they're cofunctions, and their derivatives are opposite cofunctions. Same relationship with secant and their derivatives. So really, I point this out just as a way of saying that the only derivatives you really need to remember are sine, tan, and secant. And if you know those, then you know the derivative of their cofunctions, just the opposite sign and the cofunctions. And really, you don't have to remember any of these, because you can derive them just the same way that we have derived them here. So now we have taken the derivative, we've seen how to take the derivative of all polynomials, of all rational functions, and of all the trig functions. So all we have left at this point are the derivative of inverse trig functions, log and exponential functions, and then we're done. And then we can move on to some of the fun things that we do with all these derivatives. So that's the end of Chapter 3. Next, we got Chapter 4 coming up. See you then.